And the moment is right now. So if you did watch part one, and now you're looking at part two here, moment's up. We're ready to rock and roll now with some more challenging type problems. All right, so carry out the indicated operation and write your answer using positive exponents only. So we looked at problems like this in section 1.5 when we worked with exponents that were integers. The only difference now is you're going to have some fractional exponents to contend with. Okay? So let's go ahead and get started. We have to know our properties of exponents. All right, so what is this going to equal? Well, let's see. Again, more challenging because of fractional exponents. Let's see what we got. We got a 2/5 and we got 4/5. So when we divide these like bases, now because they're fractional exponents, we have to make sure we have a common denominator. Okay, so we do have a common denominator here and here. It's 5. And so which exponent is greater? Is it the 2/5 or is it the 4/5? Well, 4/5 is greater than 2/5. That means the base x right here will remain in the denominator. Okay, how much greater is 4/5 than 2/5? Well, it's 2/5 greater. So you write x to the 2/5 again in the denominator. This x we have not messed with yet. So x to the negative 2/3 stays as x to the negative 2/3. Now, look, you can't really use that little trick that I taught you in section 1.5 by comparing the two exponents. I mean, you can. I mean, in a way, you know this is greater than that. So you know that your base x will remain in the denominator, okay, when you're finished. So with that being said, though, do you know how, like, real quick, how much greater 2/5 is than negative 2/3? Well, maybe some of you do. And you can use your calculator to do that as well. But let's just do this. Let's just follow the property of exponents that states what? When you divide like bases, you subtract the exponents. So what that means is you rewrite the numerator exactly as it was originally written. And then in the exponent position, you write down minus and then whatever this exponent is that the base is being raised to in the denominator. So minus 2/5. Okay? All right, so what do we get? We get x to the, well, if we don't have a calculator, we have to come up with a common denominator. Think back to grade school. Look at the exponents there. We have to be able to subtract 2/5 from a negative 2/3. Okay, so the LCD here, looking at 3 and 5, would be what? 15. Okay, so if it's 15, excuse me, if it's 15, that means we have to multiply this 3 by a 5. So 5 times negative 2 is negative 10. And then in a similar fashion, this becomes a 15. What times 5 gives you 15? 3. So this is going to be a 6. Let's add the opposite there. And ultimately, you get this, negative 16 over 15 in the exponent position, which is the same as 1 all over what? Remember, you can't have negative exponents. So you end up with this. Now, we end up with this 1 over x to the 16/15. However, things are getting more complicated here. This is fine for now. But we are going to revisit this problem once we learn how to rationalize the denominator. We're going to do that in just a little bit. All right, we'll do that later on in this section. But for now, this is fine. Okay, so moving on to number 2. Well, I'm not going to mess with this 3/2 in the exponent position right now. I'm going to identify, oh, I'm dividing like bases within the parentheses. So I can go ahead and do that since it's all inside the parentheses. I don't have to worry about this exponent just yet. So here's what I'm going to do. I'm going to keep the parentheses intact here. Keep the 3/2 the same. And I'm going to keep the 4 there and the 9 there. They don't reduce. And now I can go back to what we did do in section 1.5, that little technique again. I'll go over it with you one more time. So which exponent is greater? The 6 is. That means base A will remain on top. How much greater is 6 than negative 3? It's 9 greater. Boom, done. Okay? And look at the base B's. Which exponent is greater? Negative 2 is greater than negative 8. Therefore, base B will stay in the denominator. How much greater is negative 2 than negative 8? It's 6 greater. So this is where we currently stand. Again, if you wanted to work this out like we did right here, that's what you're really doing anyway, you're more than welcome to do that. Doesn't matter to me. I just think it's quicker if they're nice integer values to do it the way I just did. All right, at this point, this entire quotient is being raised to the 3/2, which means the following. Every single part of this thing is going to be raised to the 3/2 power. So this is what it would look like. 8 to the 9th to the 3/2. We already did that. Let's see, in the denominator, the whole 9 to the 3/2. And then b to the 6th, that whole base, to, again, the 3/2. All right, so if you want to use your calculator for this, you can. Or this is the same as 2 squared. 2 squared to the 3/2. 2's cancel, right? 2 cubed is 8. Again, the numerical components, I would recommend you just use your calculator. Let's go ahead and do this one. So nothing reduces here. So power of a power, you multiply. So you get 8a to the 9 times 3, that's 27, all over 2. And that's okay. That's okay. That's correct now in your numerator. Okay, moving on into the denominator. 9 to the 3/2. This is really the same as 3 squared. So 3 squared to the 3/2, 2's would cancel because you're multiplying exponents. Then 3 cubed would be 27. Again, if you don't understand that, for the numerical components, you can just use your calculator. All right, this one. Well, we can reduce here if we want. 6/2 is 3. 3 times 3 is 9. So you get b to the 9th. If you don't want to reduce, just multiply. Again, you're allowed to use a calculator. 6 times 3 is what? 18. Then divided by 2, you get 9. And we're finished with example number 2. All right, moving right along. The next thing we want to talk about here in section 1.7 is simplifying radicals. Here are the properties of nth roots. All right, they're very similar to the properties of exponents. It just, instead of being in exponential form, they are in radical form. All right, number 5 here, don't worry about. I won't try to trick you with that. Okay, obviously this is a property, but I'm not going to have a question like that on any test, so don't worry about it. All right, so ultimately we need to be able to use this information, and you can pause it if you want to study it, but I'm going to go over these properties by way of example. Okay. But obviously, you're welcome to pause the video at any time to take some more notes on whatever you're seeing. Okay, so be able to express result in simplest radical form. We got to know that. SRF, simplest radical form. Okay, so we're going to use these properties to help us do that. All right, so let's go ahead and get started. In order for something to be in simplest radical form, the following 4 criteria must be met. Okay, these conditions. All right, they have to be satisfied. So you can pause the video if you like and take a look at these, but I'm going to go ahead and answer this question. All right, so number 1, is number 1 in simplest radical form? Well, no. Why not? Why is the answer here no? Well, look at number 1. The powers of all factors under the radical sign are less. The powers, there's a power, of all factors, there's x to the 4th. So is this exponent, what number 1 means, is this exponent under the radical less than the index? No, 4 is greater than 3, so it's already no. Also, it violates condition number 3 because you have a radical in the denominator. So technically, you cannot have a radical in the denominator. That's why we have to go back and revisit this question in just a little bit, once we learn how to rationalize the denominator. Okay. Is this one in simplest radical form? Well, is this less than that? Yes. Is this reduced all the way? Yes. Is there a radical in the denominator? No. Do we have a fraction within the radical? No. So this is actually in simplest radical form. We have met all 4 of these criteria. This is an example of an expression that is in simplest radical form. Okay, what about this one? Well, look at number 4. Do you have a fraction appearing within a radical? You do have. So this one is being violated because you're not supposed to have no fraction. You're not supposed to have any fraction within a radical. All right, so immediately this one is no. Okay, now we could simplify this, but just based upon how it is, the answer is no. Okay, so let us put these in simplest radical form. All right? So, number one, what we have to do here is figure out, well, one way to do this is come up with the factors of 20, the prime factorization of 20, and then everywhere you see a pair of numbers, because it's of second degree understood, it's the index is 2 understood right there, right? For every 2 you see, you're allowed to pull out whatever that value is, whatever that base is, one time in front of the radical. So that one's already finished. Again, because it's 2, because the index is 2, you're looking for factors that repeat. For every pair of factors that repeat, you're going to pull one of those factors out in front. Another way to look at this, if you want to, is to come up with the greatest possible perfect square, which is 4. So this is an alternate way of doing the same thing. And then this is the same as what? The square root of 4 times the square root of 5. Square root of 4 is 2. Radical 5, you get the same thing. All right? Okay. Number 2. Same idea here. We're trying to come up with either the prime factorization of 216, okay, which let's go ahead and do that. Let's review. How do we come up with the prime factorization of 216? Let me just go over here and write this down. You might remember this from algebra. So you're able to use your calculator. Just put in 216. It's even. Divide by 2. And you get this. Okay, divide this by 2 now. Okay, and you get this. Divide 54 by 2. And you get 27. Now it's odd. So try dividing it by 3. Okay, 3 times what? 9. And you can use your calculator to help you with this. Just keep dividing. So this is the prime factorization of 216. Okay? So going back to our problem, we're trying to put it in simplest radical form. The index is understood to be a 2, which means with respect just to the 216, we have to do what? Come up with pairs of like bases. So we have a pair of 2s, and we have a pair of 3s. So for each pair of these factors, you're going to write that factor down one time in front of the radical. So far we have this. We have a pair of 2s, so that's put 1 2 in front. Then we have a pair of 3s, put 1 3 in front. It's times 3. And then anything left over, don't forget, anything left over will remain under the radical. So far, I'm going to leave a space right here. I'm going to leave a space right here, okay? So far, we have this. 2 times 3 underneath, okay? We're building our simplest radical form solution here, okay? Our expression, I should say, not a solution, our expression. All right, so the next thing we're going to do is look at the variable components. This normally is easier because you don't have to worry about factoring any specific number. All you got to do is look at the exponent. All right, so this is x cubed. All right, so this means there are 3 x's. All you got to understand is that for every 2 x's you have, you're going to pull 1 x out in front of the radical. So you have 3 x's, right? You have 3 x's, which means, here, look. This x cubed means the same as what? X cubed means the same as x times x times x, right? For every pair of this base x, you're going to write down an x in front, okay? So times x. Now you have 1 left over. Don't forget about the 1 you have left over right there. Whatever's left over stays underneath the radical, okay? And now let's move to the y's. So y to the 4th, you have 2 pairs of y's, right? You have 4 y's, so 2 pairs, which means you have y squared out in front, okay? And then all you got to do now is simplify. So right here becomes 6xy squared times what? The square root of 2 times 3, 6x. And there you go. This is now complete for question number 2.